Hello everyone, I am Madam Leong. Meet you again in this video session. I'm delighted to be here. I would like to take this opportunity to share some information with you and guide you in preparing a good scientific report for experiment 4. The title of this experiment is Rotational Motion of a Rigid Body. Please write your experiment report in the lab report writing section provided in the physics practical workbook. The learning outcome of this experiment is to determine the moment of inertia of a flywheel. A warm reminder, all the values shared under the observation are just for your reference to ease in explanation. You are not allowed to copy and use the values for your experiment report. Any values found the same in your experiment report are against the scoring rubrics, as no plagiarism is allowed. Another warm reminder, you must write your own lab report. You are not allowed to copy your peers' experiment report. Any doubts found in the originality of your experiment report are against the scoring rubrics, as no plagiarism is allowed. The lab report basically must consist of experiment title, learning outcome, observation, discussion, and conclusion. Let's begin with the observation. Roman 1. Data tabulation. Make sure the measurement of the diameter of the axle, the calculation of the radius of the axle, and the measurement of the fixed height or falling distance of the hanging slotted mass are recorded under the data tabulation. Make sure all the column headers are labeled properly with correct physical symbols and units. The mass of the hanging slotted mass is recorded in the data table without any measurement or calculation. Therefore, the column header of the mass is written without the sensitivity of the measuring instrument. However, the unit for the mass needs to be converted from gram to SI unit kg because we are using the value of the mass to calculate for the tension in the string, which is in SI unit newtons. The time recorded here is an example of primary data. The time was recorded using a stopwatch. Therefore, the column header of the time is written with the sensitivity of the measuring instrument, which is the stopwatch. And the sensitivity of the stopwatch is plus minus 0.01 second. And it consists of 2 decimal places. Therefore, the time recorded in the data table must all consist of 2 decimal places as well. The values of average t that calculated are rounded off to 2 decimal places, same as the primary data. And the linear acceleration is obtained using the formula of 2h divided by t average square. The value of h that substituted is of 4 7 figures, and the values of t average that substituted is of 3 7 figures, and the least number of 7 figures is 3. Therefore, the values of a calculated are rounded off to 3 7 figures. The values of alpha and t, which are used for plotting graph, are rounded off to consistently 2 or 3 decimal places. Roman 2. Calculation of the centroid point. The centroid point is the mean position of all the data points to be marked on the graph, especially in a straight line graph. Therefore, we need to calculate the average value of the x and the average value of the y. In general, the coordinate of the centroid point is written as the average x and average y. We are plotting graph of alpha against t, where alpha is for the y-axis and t is for the x-axis. Therefore, the centroid point of this experiment is written as the average t and average alpha. Please show the calculation of average t and average alpha in your experiment report. Therefore, the centroid point for this experiment is 2.10 and 15.97. Remember to mark the centroid point on the graph of alpha against t, then circle it to differentiate the centroid point from other data points. Roman 3. Plot graph of alpha against t. Use appropriate scales for both x and y axes. For example, in a multiple of 1, multiple of 2, multiple of 5, or multiple of 10. From the equation 4.3, there is a negative y-intercept term in the equation. Therefore, remember to leave some space below the origin to look for the value of negative y-intercept. We need to use this value for the calculation of the uncertainty of the gradient of the graph later on. The size of the graph is at least 50% of the graph paper. Then label the x-axis and the y-axis correctly with the correct units in brackets. Write down the title of the graph on the graph paper, which is Graph of Alpha against T. Calculate the centroid point and mark on the graph paper, then circle it, followed by the marking of the other 6 data points, 1, 2, 3, 4, 5, 6. Then draw a balanced specific line through the centroid point and as many data points as possible. What does it mean by a balanced specific line? A balanced specific line is drawn through the centroid point and as many data points as possible. For this experiment, the straight line passes through a centroid point and 2 data points. However, there are 4 data points which are deviated from the best fit line. 1, 2, 3, 4. There are 2 data points which are deviated from the best fit line below the centroid point. There's one on the left-hand side of the graph, another one on the right-hand side of the graph. The distance deviated from the best fit line for data point 1 is almost the same as data point 2. Therefore, the 2 deviated data points 1 and 2 are almost balance each other. There are another 2 data points which are deviated from the best fit line above the centroid point. The distance deviated from the best fit line for data point 3 is almost the same as the distance deviated from the best fit line for data point 4. Therefore, these 2 deviated data points 3 and 4 almost balance each other. This is the concept that we used to draw a balanced best fit line. If the red straight line is drawn as a balanced best fit line, it is incorrect and not balanced. Why? Even though the red straight line passes through a centroid point and 2 data points, there are also 4 data points deviated from the red straight line. 1, 2, 3, and 4. However, the 2 deviated data points, 1 and 2, below the centroid point are both lying on the right-hand side of the graph. There is no data point on the left-hand side of the graph. Therefore, the 2 deviated data points 1 and 2 do not balance each other. There are another 2 data points deviated from the red straight line above the centroid point. Both the deviated data points 3 and 4 lie on the left-hand side of the graph. There is no data point on the right-hand side of the graph. Therefore, these 2 deviated data points 3 and 4 do not balance each other as well. This is why the red straight line is not suitable to be drawn as the balanced best fit line. To calculate for the gradient of the graph, we must draw a right angle triangle. The triangle of gradient cannot be too small. Both sides, x and y, must be at least 8 cm in length. Then label the coordinates of the triangle on the graph. We will use them for the calculation of the gradient afterwards. Roman 4. Determine the gradient of the graph. The formula of the gradient is given by y2 minus y1 divided by x2 minus x1. y2 and y1 are the y coordinates of the triangle of gradient, whereas x2 and x1 are the x coordinates of the triangle of gradient. When we want to substitute the values of y and x, how many decimal places should we write for each of the entry here? Let's continue here. For the operation of addition and subtraction, the number of decimal places of the x and y entries must be consistent. How many decimal places shall we consider for the x and y values? It depends on half of the smallest division of the scale used for both x and y axes. What does it mean by half of the smallest division? What is the half of the smallest division for the y-axis? Please refer to the enlarged graph on the right-hand side. There are 5 divisions between the values of 0 and 2. So what is the value for each of the division or each of the square box here? We take the value of 2 divided by 5 division. So each division is of 0.4, the value. And we can estimate until half of the division or half of the square box here. So we divided the value of 0.4 by 2 and it gives us a value of 0.2. And this value has 1 decimal place. So which means all the y entries must consist of 1 decimal place. So when we substitute the value of y into the formula of the gradient later on, it must consist of 1 decimal place. For the x-axis, there are 10 divisions between the values of 0 and 0.5. What is the value for each of the division? We take the value of 0.5 divided by 10 divisions. So each of the division gives us a value of 0.05. And we can estimate until half of the division or half of the square box here. Therefore, we take the value of 0.05 divided by 2. And it gives us a value of 0.025. And it has 3 decimal places. Which means when we want to substitute the values of the x coordinate of the triangle of gradient to the formula of the gradient, each of the x entry must consist of 3 decimal places. The values of y2 and y1 that substituted consist of 1 decimal place, whereas the values of x2 and x1 that we substituted, each one of them has 3 decimal places. Since all the values of x and y are in SI units, no further unit conversion is required. Then we use calculator to calculate for the value of the gradient. The value shown by the calculator is 10.118118. When we want to transfer the value from the calculator to the lab report, what shall we write? Shall it be rounded off to 10, 10.2, 10.18 or 10.182? How do we make decision? The value of the y entries is divided by the value of the x entries in order to get the value of the gradient. For the operation of multiplication and division, the least number of significant figures of the x and y entries is considered and reflected in the calculated value of the gradient m obtained. Back to the values of y and x. 25.6 has 3 significant figures. 3.2 has 2 significant figures. 3.050 has 4 significant figures. And 0.850 has 3 significant figures. Among the x and y entries, 3.2 has the least number of significant figures, which is 2. But 2 is 2 less, can be allowed to add one more significant figure, becomes 3 significant figures. Therefore, the value of m is rounded off, becoming 10.2 per kg per meter, and 10.2 consists of 3 second figures. Roman 5. Determine the uncertainty of gradient del m using Excel. You may access to the Excel for the calculation of the uncertainty of the gradient del m by using the desktop PC available in the physics lab. You need to fill in the column X with the values of t and make sure all these values that you fill in are in SI unit. Then, fill in the value of the gradient m obtained from the graph. Step 3. Fill in the value of y-intercept obtained from the graph. And lastly, fill in the column y with the values of alpha and make sure all these values that you fill in are in SI unit. Then, press enter. The uncertainty of the gradient will be shown by the Excel. Please record it down in your workbook. Please round off the value del m to the same decimal places as the m obtained. From Roman 4, the gradient that we calculated is 10.2 per kg per meter. It consists of 1 decimal place. Therefore, the del m that we obtained from the Excel is rounded off to 1 decimal place, becomes 0.2 per kg per meter. Thus, the result for the gradient is 10.2 plus minus 0.2 per kg per meter. Both the values of m and del m consist of 1 decimal place. Roman 6. Determine the moment of inertia of the flywheel. Refer to the equation 4.3. The equation of the angular acceleration alpha is given by this expression. Comparing it with the linear equation y equals to mx plus c, where the alpha is the y and tangent t is the x, and the negative tau over I is the y-intercept, and the formula of the gradient m is given by r over I. Rearrange the formula of the gradient. Therefore, the moment of the inertia I is given by r over m. Substitute the value of r, radius of the axle, and the value of the gradient of the graph into the formula. As a result, the moment of the inertia of the flywheel obtained is 2.39 times 10 to the power negative 3 kg meter squared. Roman 7. Determine the uncertainty of the moment of inertia of the flywheel. The formula of the moment of inertia of the flywheel obtained in Roman 6 is given by I equals r over m. Substitute the radius of the axle r with half d as we measured the diameter d, and the error in the measurement of diameter will cause the uncertainty in the final result. Therefore, the I can be written as d over 2m. Based on page 2 in the Physics Practical Workbook, deduce the formula of del I using the combination of uncertainties. As the formula of I is given by d over 2m, it involves division. Therefore, the combination of uncertainties can be written as del I over I equals del d over d plus del m over m. As a result, del I is del d over d plus del m over m multiplied with I, the moment of inertia of the flywheel. By substituting all the relevant values, the result of del I is 0.05 times 10 to the power of negative 3 kg meter squared. Round off the values of del I to 1 second figure. Roman 8. State the result obtained. The result obtained for the moment of inertia of the flywheel is 2.39 plus minus 0.05 times 10 to the power of negative 3 kg meter squared. The experimental uncertainties should be rounded to 1 second figure, and always round the experimental result to the same decimal place as the uncertainty. The value of the del I obtained is rounded to 1 second figure. After rounding it off to 1 second figure, it consists of 2 decimal places. Therefore, the experimental result is rounded to 2 decimal places, becomes 2.39. Finally, Both the values of I and del I consist of the same number of decimal places, which is 2 decimal places.
How many digits should be kept? Experiment uncertainties should be rounded to one significant figure. Experiment uncertainties are by nature inexact. Uncertainties are almost always quoted to one significant digit, which is the digit 5 in this example. The two zeros in front, the digit 5, are not significant. If the uncertainty starts with a 1, some scientists quote the uncertainty to two significant digits. For example, plus minus 0.0012 kg. The uncertainty recorded here, 4.1, is incorrect because it consists of two significant figures. It should be rounded to one significant figure, which is 4. Always round the experimental result to the same decimal place as the uncertainty. Example 1. The experimental uncertainty, after being rounded off to one certain figure, it consists of one decimal place. However, the experimental result shown here consists of 3 decimal places, which is not the same as the uncertainty, and it is not acceptable. Therefore, we need to round off the experimental result to become one decimal place, which is 1.2, and right now experimental result is having the same decimal place as the uncertainty, which is one decimal place. Example 2, the number of decimal places for the uncertainty is 2 decimal places, but the experimental result consists of 3 decimal places, which is not the same as the uncertainty, and it is not acceptable. Therefore, we need to round off the value of the experimental result to become 1.24, and right now it is having the same number of decimal places as the uncertainty, which is 2 decimal places. Roman 9. Calculate the percentage of uncertainty. The percentage of uncertainty is given by the formula of del I over I times 100%. Substitute the value of del I and I into the formula and multiply with 100%. The result that we obtain for the percentage of uncertainty is just 2%, which is less than 15%, which means the result that we obtain for I plus minus del I is acceptable. Discussion. Roman 1. State the result obtained in the form of I plus minus del I with the units, and state also the percentage of uncertainty. Roman 2. State at least 2 possible errors occur in the experiment and elaborate them. And Roman 3. State at least 2 precaution steps taken in the experiment. Last but not the least, the conclusion. State whether the learning outcomes or the objectives of this experiment could be determined by the experiment. A warm reminder. Please check with your lecturer when to submit your experiment report, as your lab report will be evaluated based on the report writing skill scoring rubrics provided in the physics practical workbook. That's the end for this video session, and thank you for watching.